Thank you, Peter. Thank you for having me there. They can give a talk, or let's say a progress report on what we did in the past on this question of how to deal with spherical Fibonacci points. Let's say first that is a joint work with Joseph Dick from UNSW in Sydney and Yuan Xu from the University of Oregon. And actually we work on this problem since a couple of years now. What I want to tell you here is what we did so far and what was the recent progress. Well, first, before I can start, I should say something about the Fibonacci lattice points themselves. Why Fibonacci lattice points? Because they easily describe most of the calculations we have actually can be easily extended to other kind of lattice points. So the computations are generic enough that you don't need to have in particular Fibonacci points, but they are nice to use as a standing example. And also they have very good properties. So here is the definition of the Fibonacci sequence and the Fibonacci lattice. So that's the usual way, I think, to do that. So we consider here, for example, an example with little n is 15. This means we have 610 points here, and that is one example of a Fibonacci lattice in the unit square. And well, known results, there are known results, in particular optimal results. So a well-known result is that the discrepancy, discrepancy in the unit square, the infinite discrepancy, is of optimal order here. Notice that I'm using here the normalized discrepancy. So that means that on the right-hand side, there appears this factor 1 over the number of points. Usually the number of points is included in the definition of the discrepancy. So we have optimal order for this, and then we have optimal order for the L2 discrepancy as well, which goes back to a paper by Billy, Demniakov, and Yu from 2013. This means there are very good reasons why we should look at the Fibonacci lattice point set and try to find out if they also do well if I map them to the sphere. So those are results for discrepancy. And there's also a result by Eike Hinrich and Jens Oetteshagen about the quality of Fibonacci lattice points with regard to numerical integration. So I want to mention that it's another motivation to look at Fibonacci lattice points because they are optimal in this context. And I want to point out that also quite a recent paper here, which builds on another paper that we used to argue that lattice points are very well to consider. So this is a recent paper by Ben Sporter on arXiv, who is characterizing the rational and irrational two-dimensional lattices. So that's something which I haven't really had time yet to look into, but the computations there are kind of related to what we do on the sphere. So there might be some connections which we have to explore more in the future. Okay, so that's a motivation for why we use Fibonacci lattice points. And in order to get spherical Fibonacci points, we have to define a map from the unit square to the sphere in R3, so the unit sphere. And well, we use this area preserving Lambert transformation defined here in the following way, that we map the point at the lower left corner of the unit square here, indicated with my mouse. I hope you can see that, to the north pole of the unit sphere. Why? That's kind of a convention that this makes computations more easier, because the expressions you see there, some appear to be more natural. On the other hand, you lose also nice properties or this formula is more complicated than if you consider that the points you map from the unit square to the unit sphere have the property that they are symmetric with respect to the z-axis. So with respect to the third component here, with regard to the 0 on the z-axis. So that may be useful if you want to compute certain things. So this is more awkward than this formula, but we use this formula here, and sometimes I regret that they do it this way. But once you start with one formula, you cannot mix and match then this anymore. So here are the expressions we get for the coordinates of the spherical Fibonacci lattice points. And then we collect those points into a set, which is then the spherical Fibonacci lattice point set on the unit sphere. So, well, here you see an illustration of what happens to the points we have seen before. This gives this configuration on the unit sphere. The red dots indicate the red dots ahead there. So what happens with the North Pole, what happens with the first few points. That gives some kind of orientation. Okay, so then we have our capital Z Fn as a notation for the spherical Fibonacci lattice point set with Fn points. Okay, so we know, of course, for a long time that those points are asymptotically uniformly distributed, or the sequence of point sets is asymptotically uniformly distributed on the unit sphere. For these two in this case, I did here that more general definition, and that means that this ratio of the number of points lying in a Riemann measurable set divided by the number of points will approximate the area or the volume of the Riemann measurable set. And well, that's the definition. And in order to quantify that, we can look at other quantities. And I'm not going to define them, that are not the primary focus of my talk. So I just hope that you accept that well, we know these quantities, the two-hit discrepancy and the infinity discrepancy. And as far as I'm aware of, that's the best possible quantitative result we have. So that's something which Christoph Eisler and myself and Joseph Dick proved in 2012, that the infinity discrepancy can be bounded by a constant divided by the square root of the number of points. Unfortunately, that is not. Yes, somebody raised a hand.
So please, Werner Kraut, if you have a question, then please ask it. If this is the reason why you raised your hand. It possibly was an accident, then please continue.
Okay, so this is the bound we have, and unfortunately this bound is not that great, because it can be also shown that IID uniformly distributed on the point on the unit sphere have expected discrepancy of 1 over the square root of the number of points. So we do not, the bound we have does not beat the bound of the IID uniform distributed point set on the unit sphere. So a breakthrough would be already if you can be better by an epsilon in the power of the number of points. The numerical evidence for the infinity discrepancy, well, in the paper of 2012, we did some ad hoc calculations. So we estimated the infinity discrepancy. Nowadays, there are indeed algorithms which you can use to compute that infinity discrepancy for a given number of point set, or for a given point set. So, and we could see that that's a power of log. Well, I mean, the number of points we had cannot really tell if there's a power of log or not, but it seems reasonable to say that there's a power of log divided by the number of points to the power 3/4. So that's and this power would be then optimal power for the infinity discrepancy. So in a sense, this seems from a numerical point of view, this Fibonacci points seem to be optimal up to a log factor in the discrepancy. Also, this is a list of numbers for computation of the L2 discrepancy. That can be also done exactly simply by means of Stochastic invariance principle, which says that the L2 discrepancy squared can be computed with the help of the sum of all mutual distances, Euclidean distances of points on the sphere. And that means here I could go up to over 2 million points. And it seems to look like that the right power of the number of points multiplied with the discrepancy would go to a number. So that seems to stabilize, but of course, this is not enough numerical evidence to see if there's a log power present. So, but it indicates at least that we could have a conjecture of the kind of well, the big O is some power of log of the number of points divided by fn to the power 3/4. So that just to indicate that there's a huge gap between what we can do in theory for a constructive point set, so for a sequence of constructible point sets, and what the numerics would tell us about what actually we should expect from that. Okay, so why Weyl sums? So let me first define this here, show this here. It's well known, you can find this in the book by Kuipers and Niederreiter, that the uniformity of point sets on a sphere can be also characterized by the fact that this sum here goes to 0 for every Legendre polynomial PL, and this normalized by this factor 1 over the number of points squared, we call the Weyl sum for the point set, and this has this index, the degree of the polynomials, and we want to, we are interested in explicit expressions as well as asymptotics as little n goes to infinity, which means the number of points goes to infinity. So because those Weyl sums are building blocks in the expansion of the L2 discrepancy, have something to say about hyperuniformity properties, etc. So they are very interesting in this regard. And now, well, what can I tell you about the numerics? So what I did here is, as you can see, I set or choose number of little n to be 9. So this means it's a very small point set, just 34 points on the unit sphere. But I wanted to know what happens if the degree of the Legendre polynomials cover a large range of values from 1 up to 500 times the number of points. So you can see here at the beginning, and actually I have to zoom into that to give you more details there. So there are rather large values, and then it somehow starts to stabilize around a certain value, which will become smaller as the number of points increases. So we have only one example here. I did several, and the problem is if you compute that, and I used Mathematica for that, in order to get reliable numbers, you have to do high precision computations. So I had to choose accuracies in the thousands to actually get something reasonable out of that. And as the number of points increases or little n increases, so even if it's only increases by small values, the accuracy goes up rather fast, which means that gives you, at least gave me a boundary of what I could do with Mathematica to look at that. So you see here that for a large range of the degree, the value of the normalized Weyl sum is rather constant, and something seems to be happening at the beginning of this interval for this range of the degree. And let's zoom in here. So I'm doing this in two ways. I zoom in the way that I only show you now degrees from 1 up to the number of points, and also I am increasing the number of points on the sphere. So because I do not go out to 500 times the number of points with my degree, actually I can do more points on the sphere. And you see here that there is something going on at the very beginning. So there are very small values, and then there's a large oscillation starting, large with respect to what you get here. You see that are rather small values, and this oscillation starts to die down until it, well, stabilizes, as we saw in the previous picture here. So that's what the grand picture of what's going on with the wire sums. And if I zoom in more to the beginning, then you see here that's just for the degree of the polynomials going up to the square root of the number of points. There you have very small values compared to what you would get in this oscillation part. So it's just before this starts to go up here, also for a different number of little n here. So I'm already increasing again little n to get more points on the sphere to have a better idea if this is something which works in the asymptotic sense. And this gives you rather small values at the beginning. So you could have maybe think about, well, this Fibonacci, spherical Fibonacci lattice points try to simulate spherical designs, because we know that up to the square root of n degree spherical designs give you 0 then for the Weyl sums, and starting from there, then you get non-zero values. Of course, we don't have spherical designs here, but this seems to show that we get rather small values for the Weyl sums for the range of the degree of the polynomials between 1 and the square root of the number of points. So this is the numerical picture I have in my head if I think about Weyl sums. Okay, you can do estimates, and one coarse estimate is this here. That's really a coarse estimate, which simply works with the Legendre polynomials themselves. So the Weyl sum is bounded by two terms. One term is in terms of the number of points, the other one in terms of the degree of the polynomial. And if you want to balance those two terms in terms of asymptotics, then you see that actually this the second term is dominant for smaller values of L, and the first term becomes dominant for larger values of L, and large really means square root of the number of points and more. So at first glance, this doesn't look like very useful. However, we could show that if we plug this estimate into the expansion of the sum of distances, then this gives us control over all the terms with degrees larger than the number of points, not just the square of the number of points, but the number of points. So this means that actually we have control over the tail in the L2 discrepancy expansion. These are just side remarks, so I'm not really going to show these results here. So this is not that bad in this regard, but if you only concentrate on the Weyl sums themselves, then it's not that good an estimate. And the reason is because one has to deal with this products here, and even if you want to use some geometric properties, it's very difficult to incorporate them so that you can make use of that if you want to improve your estimates on the estimates for the Legendre polynomials. So this means we have to look for something different to do that, and that means actually I can try to reinterpret this Weyl sums in terms of numerical integration errors. That's also something we, well, it's quite easy to understand why this has to be the case. So we have this addition theorem for the Legendre polynomials, which, if you slightly modify that, is also the addition theorem for the spherical harmonics. And the FLM are up to a normalizing, up to a multiplying normalizing factor, which has to do with the dimension of the space of homogeneous polynomials. You have a spherical harmonics in front of you. So we have this identity where we can express the Legendre polynomials in terms of this sum of the functions FLM. And then we can use properties of the associated Legendre polynomials PLM to actually rewrite this as a sum of squares. So the number, the not normalized form of the Weyl sum is simply a sum of squares, and these squares have an interpretation as numerical integration errors. The Zm is simply 1 if we have little m is to be 0, which means that in this formula we have here the Legendre polynomials. It becomes 2 if we deal with the associated Legendre polynomials. So what are those expressions in this square here? Well, first of all, you can see that the sum with the Legendre polynomials is just a Riemann sum approximating the given integral with respect to equally spaced nodes. So this integral is 0 because of orthogonality properties of the Legendre polynomials. So in fact, we measure here the error of numerical integration with this sum of Legendre polynomials. And similarly, we can also interpret the other expression as an error of integration, but now as an error of integration for the function FLM in the unit square. So that's called a Fibonacci lattice rule, which allows you to approximate a double integral of the function on the unit square. And again, the function we have written up at the beginning is such that this integral becomes 0. So we are measuring the numerical error here, and this means that we have that the Weyl sum is a sum of squares of numerical integration errors. So then we can try to find out formulas for these numerical integration errors to say something about the Weyl sums. Okay, so the easy part, well, this has to do with the Riemann sums of the Legendre polynomials, of course. Why it's easy? Because I can give you explicit formulas. They are not that difficult to obtain. For that, I need Pochhammer symbols and Bernoulli polynomials. I'm summarizing here some of the properties that will be used here, and in particular that the Bernoulli numbers are 0 if k is at least 3 and an odd integer. That means that in a sum where those numbers appear, all the odd terms disappear when the index is sufficiently large. Well, it turns out that the numerical integration error for the Legendre polynomials is simply 1 over the number of points. That's the symmetry argument, so there's nothing to compute there. If L is odd, and this given expression for even L. That's an application of a generalized Euler-Maclaurin summation formula, which can be used to compute this explicitly. And this is actually a asymptotic representation of the ELN if we assume that L remains fixed. So there is a setting where you do this, namely if you consider hyperuniformity questions, then there's something which is called a structure factor, and there you do fix the degree, and then you let n go to infinity. So that means in this setting we can actually get asymptotics for this contribution to the Weyl sum in the structure factor. Okay, proof, as I said, is this application of the generalized order Maclaurin summation formula. I had to search the literature a little bit to find this formula, but you can find this there as well. And in particular, I didn't compute that for the Legendre polynomials at k divided by n with omega is equal to 0, but for arbitrary omega between 0 and 1, which does this, which means that actually I'm looking at a lattice which is slightly moved in the vertical direction. So that means that instead of having a point fixed at the North Pole on the sphere, I'm moving this point away from the North Pole, and indeed this increases the order, or makes the order in n better. So in particular, if omega is a half, which means that we have again a symmetric situation. Before that, if I have omega is 0, we also have a symmetric situation if I delete the North Pole point, because then the z coordinates are symmetric with respect to the xy plane. So we have a symmetry in this sense, which explains why we have here perhaps an increase of order. This is 1 over n squared instead of 1 over n here. And if I move the lattice such that I have now this sets of points or sets of components in the z direction symmetric with respect to the 0 again, then I get that it doesn't matter if L is even or odd, I am going to start with an n squared term in my asymptotics. So this already gives a motivation to not look at the usually defined lattice, the not shifted lattice, but you should better shift the lattice a little bit so to improve the asymptotics. Okay, and these formulas can be obtained not only for omega is 1 over 2, but for any value of omega between 0 and 1. And so I know what's going on here for this part, for this contribution to the Weyl sum. Okay, what's about the difficult part? This involves this associated Legendre polynomials. And this means, well, we can try to get the coarse estimate again. So, which means that the proof idea we had here is, well, take summation by parts so that the terms over the, I have to be careful about the exponentials are added up here, and the terms where the associated Legendre polynomials appear, well, here I have to do a trick with dividing up the interval of the integral and to get this here written in a better way. So, and then we have to estimate this. And these sums of exponential can be given in closed form, so you have to estimate this. And in my course estimate, I'm doing the most simplest form of estimate. I'm estimating the this part here in absolute value by 1 and end up with this here, but I believe it's something which can be done better, in particular because Ben Sporter did a lot of this estimates also in his papers, but there he has a irrational number instead of the ratio here of the Fn minus 1 divided by Fn. So one has to consider Fn and this part together, or even Fn and this part in a useful way, estimate so they get it out of the sum here together to get a reasonable estimate for this here. So I cannot simply say, okay, 1 over Fn, that's the dominant part, everything else is bigger of 1. I don't think that this will work here. So one has to be more careful. However, this estimate still works in a way that allows us to control more terms in the expansion of the sum of distances. That means in the expansion of the L2 discrepancy. So we use that there. And well, this is not that difficult to show, but how to use that in the expansion for the L2 discrepancy, that's much more technical, which I'm not going to share here. Okay, so coarse estimates won't really help. There is a different approach, namely the Fourier analysis approach, which can be used here. And this relies on the following theorem, which is well, from these two papers by Price and Sloan from 1992 and Niederreiter and Sloan from 1994, they say that the error you do here is a limit of the sums of the Fourier coefficients over the dual lattice to the Fibonacci lattice. This is a limit here, and the function FLM is precisely of the class of function which is considered in this paper, so we can apply this result to our case as well. So, well, here I'm writing up what the dual lattice is and how to characterize it in terms of the numbers H1, H2, and Fibonacci numbers here. And well, it's not that difficult to compute the coefficients. So the part with the exponential just simplifies to the Kronecker delta here, and the other one is the more tricky part with the associated Legendre polynomials, and then we have to sum up here over, as you can see here, since we have the Kronecker delta here, we actually not have to sum up over a rectangle or a square that grows in the lattice, but we only have to sum up over horizontal lines. So M is then fixed, and then which M fixes this H2, and H1 then goes from these ranges here, or actually it can be shown that this decay rate here is sufficiently that we can actually go from minus infinity to plus infinity in the right way. So that's what I'm going to show here as well. So we can rewrite this formula by substituting a formula for the associated Legendre polynomials, end up with these integrals here, which need to be computed. And well, here I was using Mathematica so that I got an expression in terms of this regularized 0-1 hypergeometric function, which can be expressed or simplifies to a Bessel function, the Bessel J function, Bessel function of the first kind of the absolute value of h1 times pi divided by a power. In particular, if it turns out that this index here is of the form of a half integer, this becomes simply a spherical Bessel function for which you can get explicit expressions. They are kind of messy, but that would give you an explicit expression which you can then sum up with respect to the H1 here, and then therefore get an expression for this part here. And then you can take the limit or even use the infinite series summation. So this expression in terms of the Bessel function can be used to argue that, okay, oh, I haven't changed here the, okay, that is something similar to this here times where you have the cosine and sine functions of other terms in the asymptotic here appearing here, and this is in this sense an exact asymptotics, and the power you have here is sufficient because large that you can sum up over all terms in the sum, because R is at least little m, so you have here m over 2, and m is at least 2, because otherwise I cannot apply the Fourier approach here, and this means I have sufficient power here that I can sum up this. And well, what I have done, but I noticed that there was a mistake, so I don't show you that I used for this part here a Mellin-Barnes integral representation, and then summed up under the integral, which led to if the number of points is even, you are dealing with Hurwitz zeta functions, then you have to shift your your contour to the left, you either pass over a pole or not, depending on the value of Q here. And then if you are sufficiently far to the left, you can replace the Fourier zeta function with a expansion in terms of trigonometric functions and go backwards. But somewhere on this computation, I did something wrong, so I cannot show you this form. Otherwise, I could have shown you a closed formula for the numerical integration error. So I'm not really sure yet if this is going to work in the end. However, that's the progress report so far. What is the outlook? Well, there are two main topics. One topic is going in the direction of hyperuniformity. That's my going to picture. If I want to explain hyperuniformity or show you that, that's the picture on also used for this nice article, so that even laymen can understand what hyperuniformity in the unbounded setting is. And in the joint work with Peter and Werner Kastner and Jonas Ziefle and so on, we explored this also for the compact setting on the unit sphere, so that we have there also criterions what it means that a sequence of point set which is deterministic or probabilistic is hyperuniform. And one important point is there that we also have an analog of the structure factor, which is the Weyl sum multiplied by the number of points. So we don't have 1 over the square of the number of points, but 1 over the number of points. And for that, well, for that we need fix the L and let n go to infinity. So the computations I did here would help me in obtaining the or see if the structure factor does have a limit, or if it can be bounded, or what is the precise asymptotic behavior, not just 1 over the not just a constant or so, but also if this is some power of the number of points in my case, not what I am explaining here or showing you here in terms of the unbounded setting. And the other one is, of course, the ultimate question. Is it possible to get the best possible or even an improved bound for the L2 discrepancy of a constructible sequence of constructible point sets on the unit sphere? And well, the approach here is to use the last invariance principle, express the L2 discrepancy in terms of the sum of distances, expand the sum of distance in terms of wire sums, and then use the correspondence between numerical integration errors and wire sum I had written up before, and yes, and then use suitable bounds or even asymptotics, sharp asymptotics for the numerical integration errors, and that would give an answer if this spherical Fibonacci points are indeed point sets that have optimal order of L2 discrepancy, even if it's possible to get not just an order estimate, but also a limit if this limit exists. And that's work for the future. And well, I hope that we can tell you more in future talks about that and even present a result. I think that time is over, and that means thank you for your attention.